Hi everyone, in this video we will cover the CAD comparison. This is where we have nominal data, which is the CAD model itself, and the actual data, which is the program points on the CMM. We best fit certain features to the model. The software does its best to get this as low as possible, and then everything else is compared to the CAD model. This produces the heat map and is very useful for freeform profiles, but just in general, the heat maps it provides for each feature gives far more detailed ideas on form when compared to the CAD model versus the feature alone. So let's dive in. So we have used the small Aberlink test block to create a very basic measurement routine. This is a plane, circle, line reference system, and then I've measured two 3D features, a cylinder and a cone, just to show you the comparison points on a basic feature-based best fit. So let's switch this off for now, and the first thing we want to do is open the CAD software and bring the model in. So again, go to enable CAD, decide whether you're going to use dual monitors or the dock feature. So we will use the dock feature, and then we will locate the CAD model. So for anyone wanting to practice with this, if you go to C drive, program files x86 and Aberlink3D V4, the original test piece and the new test piece are both available in there as step files. So I'll open that up, and you can see here this is the CAD model for the part you've just seen on the screen. And the first thing we need to do with any CAD system, it's not as required in the CAD comparison, but it's always a good habit to get into, is to set the visual alignment. So what do we mean by that? Well, the X and Y axis of the model need to match up with the X and Y axis on the machine. This is so probe head indexes and alignments, etc., can all be correct. And we do this in the CAD toolbar via the Set Visual Alignment icon here. So we're going to click on that, and we have multiple different options for this. So the first option that it refers to is a 3-point method. So this is defining a point on a face. You would then, in relation to that point, take a point in the X positive and then a third point in the Y positive. So let's start with this method as it is the beginning method. So for example, we want the job sitting like this on the screen. So we will take a point down here. That's the origin. You see it goes green. Take a point along the new x-axis in the positive direction. So in relation to this origin point, I want to move to the right. That'll be the x positive. And then take a point in the xy plane in the positive y direction, which would be away from it, roughly about here. It doesn't have to be perfect. And you'll see there now we have alignment complete, and the X, Y and Z axis of the view block or rotation cube match up with the machine. We get alignment complete, we hit the green tick, and the visual alignment is now matching up with the program on the machine. A second method, if we go back in, is to use the CAD view. So if I sit the CAD model as if I was looking down the probe, so it's a bird's eye view from directly above, I can use this icon, which is called the component button. So press to use the model view to set the alignment. So the model view is set correctly there. So we click on this once, position the CAD model as it would be when looking straight down with the screen XY aligned with the machine XY. Press the component button, which is this. Again, when you have done this, we already have, so we press this, alignment complete. That is a second method, very useful. And if we go back in, the remaining two methods, whilst not an actual method, we can use this icon to click on a face and the model will square up. So you see, if we wanted to use this face as the alignment, you click on this icon, click on the face, and it will automatically carry out the alignment. The very last method is to use the CAD system itself. So if we close this model and bring it in again, whatever the alignment for the CAD system is, which is this here, if we go into Set Visual Alignment and click on CAD and then the red cross, it now uses the CAD-based datum and orientation system. So I'm just going to go back to the first setup, and I personally prefer to try and use the model view. So I get the model view as I want it, set visual alignment, and click the icon twice. It's this icon here, the component button, alignment complete, and that is how you set the visual alignment. We can now look to carry out a best fit. This is done through the best fit icon here, and again, as mentioned in previous videos, this will only appear if you have the CAD comparison license. So we click here and the CAD points fit window opens. I'll go through all the different icons as we go through this video, but the general idea is we are now going to use the link icon here to select features in the program, and the order is we click the feature in the program, so i.e. this plane. We would then click on the corresponding faces on the model itself. So if we click on this icon to start linking features, we go feature and then the corresponding faces on the model. This only has one face, so we can move straight on to the next feature, which will be the circle. 1, 2, this has 2 different faces on the CAD model. And then the line is this face here. Now this will define the 6 degrees of freedom and allow the software to carry out the best fit. However, you can over constrain the part if you want. The software will simply add those features in and try to carry out the best fit with all the features you have added. So you can over constrain it without any problems. At this stage, we're going to click the link. So we're not linking features anymore. And then we're going to click on this icon, a bit like the reference icon, do points fit. This will carry out the best fit. And you'll see there, on its first attempt, it had 6 iterations and it managed to get this as low as, well, the RMS error to 0.003, which is good. So we press OK, but it is worth noting that if the reference features you have used are, quite far out from the nominal on the CAD, you will never be able to get the RMS error low because the features simply do not best fit together to a nominal low size. So press OK, hit the green tick, and you'll see now the best fit hand goes green. That means the RMS has been calculated and the best fit has been completed. So just to cover the icons within the CAD points fit window. So link we've already gone through. So just to go over it one more time, you select the feature and then select the corresponding faces as so. Auto link is also useful, as once the best fit has been carried out, you can press auto link and it will match the remaining features to faces so they can be used for the fit or the compare. So that's auto link. Clear all clears out all of the offsets, or if you just left click on an individual one, you can delete one at a time via the rubbish bin or the trash can. Do points fit we've already covered. The broom with the red cross clears the existing alignment out, so you see the hand goes red and that cancels out the existing alignment. And then we have the options, which we've already covered in the previous video, but this is where we have a points fit threshold. That's the limit at which it will accept the best fit. A timeout, so this is the amount of attempts. It'll do 30 attempts before it times out, and the same with the total time. So this is 30 seconds. So after 30 seconds, it will time out. So you can mess around with these if you need, depending on your application. And then lastly, at the moment, we're not displaying the RMS error in the standard software. We can switch that on here once the best fit's been carried out. So let's just delete that, and we are going to go with clear it all out and just do the best fit again. linking features, best fit. And if we click here now, you'll see the RMS error shows up here. The RMS error is also indicated here. We also have this quality of fit score. In all honesty, it's not very useful for the end user, but generally speaking, the higher the number, the better the score. And then we have our standard apply changes and accept changes. So that is the toolbar for the CAD best fit. Now that the best fit has been carried out, we can right click on any feature. Let's take this cone for example, and you'll see it displays the measurement points from the feature itself on the CAD model, so we can see them as a kind of heat map. The view we leave with this feature saves with the feature itself, so we can mess around with the transparency or whichever layout we want or view, and this will save with the feature. But you can see the heat map points are very valuable, as the feature itself only shows us the points that fit within a cone, whereas now we can see where that cone sits within the CAD model via the best fit of the reference features, which would, ultimately be datums as well. So that is how you view the points of a feature. If we wish to adjust the style, scale or tolerance of any given feature, we can do so within the CAD tools. So right click on your feature, go to CAD tools, and the first thing we will go through is error scale. So if we open up error scale, you'll see this sets the error scale and tolerance for the feature. We have the scale here. This will display as this kind of magnifier, so it makes the points look as good or as bad via the scaled up value. So this is 1 to 1, and it can go right up to 1000. The tolerance is here, so you would put your tolerance in, 0.1 let's say, and then you have different options. You can use bands, which are simple pass-fail. So if it's within this tolerance, it's green. If it's above the tolerance, it's red. And if it's below, it's blue. If you prefer a more heat map style, you can use shades, and that will slowly fade in and out of color when it's above or below at least one tolerance. So that is the error scale. If we go back to CAD tools, we can change the markup style here. So instead of displaying the tails or whiskers as they're sometimes known, we can actually display the errors themselves. This is useful, but it is limited in that we can only fit so many values on the screen at once. So any point heavy scans, with a scanning probe or anything like this, you will only be able to display a certain amount of points using this method, which is why it generally reverts to the tails method or whiskers method like this, as you can display every single point within the feature. You can change the line width, so if you want to change the features, you can display them a little bit better with thicker lines. This is personal preference, but these are the kind of things you can use to change the displaying of the points for each given feature. You can also show the feature info within the window, so this is useful when we change back to tails. So in the graphical window itself, you have unit for cone, the XYZ position, the angle and the fit of the feature, and it goes hand in hand. It's still useful information with the heat map, and that is the show feature info icon here. So that is how you display or change the displaying of the points within the software itself. Once we have all our options optimized for the feature, we can then easily generate reports via the tabulated CAD points option and CAD graphic details options within the reports page. So if we tick tabulated CAD points, all we need to do is click add feature and select the feature that we want to display. Click add feature again when you are finished. Do the same for CAD graphic details, CGD, add feature, cone, click here, and then if we generate that report, you will see we have the tabulated CAD points now in the same style that we had selected in the options and the CAD graphic details, and again this displays not only the points but the details for the feature because we had that switched on. And these are how you generate your CAD reports. It's also worth noting that we can now verify these points as a profile here, which is useful if you have a tabulated dimensions report. So again, we had this as a 0.1 tolerance. And if we had this in a tabulated dimensions report along with other standard dimensions, you'll see it displays just as normal. You can't do this until the best fit has been done, as it has nothing to compare the profile to. So these are your reporting options. We will now cover the curve measurement. This is often used for checking profiles that are 2D. And in this example, we are going to use the slot. So I'm going to drive the probe into the pocket for the slot. We'll open up a curve feature. So this is the curve feature here. And the idea in this particular case is we are going to take 3 points, a start, direction, and end. Now this won't be the end as we want it to loop around, but the 3 points generally define the start, direction, and end. We now go to CNC. We change it from machine touch to PEC scan. If you have a scanning probe, machine scan will also be an option here. So we are going to say PEC scan. And we set a pitch, which is the distance between the pecs. So in this particular case, I'll use 0.5. And as this is a continuously closed slot, I'm going to tick the close button and hit make. The idea now is I'll lift this probe out the way and we'll press play. And the probe will take a point at my start point, head in the direction of the second point, and loop around until it gets to the end. This is a constant feedback, so after every point that it takes, it feeds back to the system and works out which distance or which way to back off to then go and measure the next point. And you'll see if you set the pitch too high, you'll sometimes cause it to crash. So you have to mess around with the values until you optimize them for your particular application. So you'll see it pecking around the slot here now. And again, this is 2D, so it's a 2D surface measurement essentially. So instead of being a 3D like a blanket, it's 2D, which is useful for pockets and slots like this. So now that we have that done, we can go in and see you have a much more detailed picture than the standard features we took before. So we'll zoom in there. Go to the CAD toolbar, change the transparency, and again we can have a little look at messing around with some of the scale just to highlight the error. And in this particular case we might want a simple pass fail on a 25 micron tolerance, and you'll see there the green points are in, blue points are low. And if we want for the report to display the entire feature, you'll be able to see that it was a curve measurement. And there we go. That is how you measure and compare to 2D profiles using the curve feature. Now we can look to utilize the surface feature. So this is used for 3D profiles and surfaces. And it works in a similar fashion, only because it's 3D, it will peck between the points that we've taken. So in this example, I'm going to measure a triangle, start point here, and then I wanted to peck over to this edge, then over to this corner of the triangle, and then back on itself over here. I would like to highlight at this stage, it's generally a bad idea to program on the machine when measuring surfaces like this, as the vectors for the contact points are generally very bad. If you program from CAD, which will be in the next video, you will see how useful it is, as the probe can work out the correct vector via the mouse points. But you know, hopefully it highlights how the function works in this video when on the machine. So we've taken the 4 points, so the 3 points of the triangle with a final point back at roughly the start. We go to CNC and we say from machine touch to PEX scan. I leave the pitch at 1, I think that this should be okay. So we press make, and then I'm just going to lift the probe clear of the safety volume and press play. And you'll see this will now step 1 millimeter from the start point over to the next point, then work its way to the 3rd point before coming back to the 4th point. So it effectively is just scanning between points. When using contact scanning, i.e. an SP25, it works in the exact same fashion. It will simply try to scan between the contact points that you have selected. So it's looping over to that point and now coming back on itself. And once this is complete, we will have the exact same options available to us as we did for the curve, i.e. the slot. So we leave this open and we can move it over here now, and you'll see we get the data points on the surface there of where they are in relation to the best fit. So again, we can hollow out this model, go to CAD tools, error scale, and display the errors however we want. This might be a 0.5 tolerance, and we use shades, and you'll see it's just personal preference on how you wish to display the feature. You may also see, as I've mentioned in previous exercises, this called out as a profile within a tabulated report. So all we do is double click the profile itself, and because the best fit was carried out through A, B and C, we can also apply A, B and C, as that is effectively what is creating the profile call out via the best fit. So that is the surface measurement and essentially 3D profile checks within CAD Comparison. The last thing we will cover in this CAD Comparison tutorial is the set model offset. This is a feature used when the CAD model isn't nominal size and you need to do comparison checks to it. It works very easily. You click on set model offset, which is in the CAD Comparison toolbar. The CAD model offset window opens. And the idea is if we right click on anything we've measured, so this curve scan for example, we can apply an offset on the points in relation to the model. You have two options. You can have an offset for all features. This applies automatically whenever you right click on a feature, or you can do it just for this specific feature. So for example, if I put a 2 mil shift in here and press apply, you'll see all the points are now too high. And the opposite occurs if I put -2. Yeah, so you can see it offsets the points on the model. And like I said, this is mainly used when a CAD model is not nominal size. It's either undersize or has specific features on it which aren't the correct size, and you can offset the points to match the drawing. So that is CAD model offset, and that wraps up this CAD comparison tutorial.